So this lesson is acid bases, definitions, and how to name acids and bases. The test over this unit will be next Thursday of next week. Okay? And so I'll let you know what that is. And we're going to do a lab on Friday. So first of all, bases are strong. Bases are going to be metal hydroxides of group 1 and 2. With the exception of beryllium and magnesium. They're actually weak. And what makes it a strong base is that it completely dissociates or completely ionizes in water. So in other words, let's say I had sodium hydroxide. When it goes into water, it would be sodium plus hydroxide separate. It completely ionizes. That's what makes it a strong base. Okay. A weak base is something that only slightly ionizes in water to produce an alkaline solution. Anytime we're making a base, it's going to make an alkaline solution. Alkaline is just another word for basic. Okay. There are some examples of some weak bases. Ammonia. Okay, that's a weird bell. I don't know why that bell's there. Ammonia is one. Sodium bicarbonate, which is baking soda, the second one. And then sodium cyanide, which is actually a poison. Those are just some examples of some weak bases. There are some of your common bases as far as strong. They're not listed in your notes, but they're all group 1 and group 2 metals with the exception of beryllium and magnesium. Okay. The most common base that we'll deal with in here is going to be sodium hydroxide. And when we do our titration, we'll be using sodium hydroxide. So then that brings us to strong acids. And strong acids, like strong bases, are ones that completely 100% ionize in solution. And they're going to make acidic solutions. Okay, and we'll talk about what constitutes being acidic or basic when we get to pH on tomorrow. So weak acids are only slightly. So they're kind of like the weak bases, only slightly. There are only 7 strong acids. I need y'all to stop talking in the back. Okay? Otherwise I will move you. Thank you. There are only 7 strong acids. You must memorize them. So write yourself a note to memorize them. You have them listed out. Although I believe the HClO3 might have gotten left off on yours. So, it's there? Okay. So I added it in. At one point it was left off. So you have to memorize those. Some of your weak acids are things like acetic acid, which is what's in vinegar. Citric acid, vitamin C, which is what makes your candy and stuff very sour. How many of you like Sour Patch Kids? Okay. What happens after you eat them for a while? What happens to inside your mouth? It starts to burn, and that's because what makes them sour is the citric acid and absorbic acid. So that's actually why, because acids taste sour. I want to make sure acetic acid, you recognize its formula. And why do I want to make sure you recognize its formula? Because it probably will show up somewhere on a quiz or a test. There are actually 2 ways to write it, and it shows up both ways, so you need to recognize both ways. And back when we were learning the polyatomics, acetate, we had to learn both ways. So that's the 2 ways that it shows up. And that is a very common weak acid. Okay, so it only will dissociate slightly. Okay, and if you remember from last unit for solutions, a strong acid makes a strong electrolyte because it completely ionizes. A weak acid makes a weak electrolyte. So, naming the type of acids, there are 2 types, and remember it was about the oxygen. The first type was a binary acid, and that is when you have hydrogen and one other element. They do not contain any oxygen. That's supposed to be underlined, not crossed out, sorry. Okay, so an example of that would be, remember HCl, how would I name that? Hydrochloric acid. Okay, so that's how we do the things without oxygen and with only 2 elements. Okay, the oxyacids are ones that are with a polyatomic ion and they contain oxygen, and that's your blank on yours. It got left off on here, but your next blank says that contain oxygen or with oxygen. So makes sense, it's an oxyacid, it has to have an oxygen present. And that's where we went the ate to ick and ite to us. Okay, so remember, if I had H2SO4, the SO4 is sulfate, and so we would call that acid sulfuric acid. So remember, we wouldn't use the hydro in there. Okay, and then if I had H2SO3, the SO3 is sulfite, so we'd have sulfurous acid. Okay, and then when you're doing the bases, they're named just like normal ionic compounds that we learned to name. So sodium hydroxide, NaOH, lithium and hydroxide would be lithium hydroxide. There's no special rules for those. They're just named like normal ionic compounds. Okay, because even though they're a base, we call them a base. They are an ionic compound because it's a metal and a nonmetal. Okay, so your left side activity on the next page is a practice of naming. Okay. There's acids and bases listed in there, so you're going to practice naming some of those for a left side activity. I will give page numbers tomorrow. I did not get them in my notebook over the weekend. Sorry. These are some properties of acids and bases. You absolutely 100% need to know the properties for a test and or a quiz. So let's talk about acids first. They're corrosive, which means they will corrode metals. They're bad. They'll burn your skin. They taste sour. We already talked about that with your sour candies. They react with metals to produce hydrogen gas, H2. And when we did types of reactions, when we had that activity series, remember where we would check if something replaced something else? Remember, hydrogen was listed in there with the metals, and that's because when you react metals with the acid, it'll replace that, kick out the hydrogen. And we've done that before when we did magnesium and acid. If you have litmus paper, it's going to turn it red. When you have phenolphthalein, it keeps it clear. And then, of course, we said they're electrolyte. Okay. Bases are also corrosive, especially if they're really concentrated. They taste bitter. Anybody, when you were a kid, have to have your mouth washed out for soap for saying naughty words? No, they don't do that anymore, man. Okay, someone finally.
No, but it wasn't for naughty words. I think I lied or something like that.
Yeah, it tastes bitter. Soap tastes very bitter. Or if you've ever accidentally gotten soap in your mouth, you're washing your face or whatever, and you accidentally get soap in your mouth, and you're like, bleh. Yeah, it tastes bitter. Okay. They react with oils to produce soap. That's why soap doesn't taste good, because it's a base. And they feel slimy, or we're going to say slippery, because the word slimy doesn't show up as much as slippery. So feels slippery. And you know that from washing your hands, right? Feels slippery. They will turn litmus paper blue. And then in the presence of phenolphthalein, which are indicators that we'll talk about a little later, they are a bright pink. They're really pretty, actually, when they're in phenolphthalein. And then they are also an electrolyte. So those are some of the characteristics of acids. You might write yourself a note and say, you need to know these for a test. Okay? You need to know these for a test. So we're going to talk about the definitions of acids and bases. There are 3 definitions, okay? You are responsible to know the definitions of all 3, okay? One of them, we literally just talk about the definition, and you got to know it, but the other one we're going to work with a little bit more extensively. The first definition is called Arrhenius, which is right below, if you don't know how to spell it, this word right here. Acids and bases. And it is the strictest definition. And by strictest definition, I mean there will be fewer things considered to be an acid or a base under this definition. It's a very strict definition. Okay? And so what the Arrhenius acid states is that it produces a hydrogen. Oh, that's supposed to be H+. That doesn't look like it, does it? Let's put that up there so you can see it. A hydrogen, also called a hydronium, which is written like this, H3O+. Okay? So when it's in a reaction or in water, it produces the hydrogen or the H3O+. Okay? You have to know what this hydronium looks like. You have to recognize that on a test. Okay? So hydronium is H3O+. Okay? Arrhenius base produces a hydroxide. Arrhenius base produces a hydroxide. Okay, so I've given you an example of the way it breaks down. Okay, hydrogen, sodium hydroxide would break down to sodium plus hydroxide. So since it produces a hydroxide, it would be a base. If I had, say, HCl, and it breaks down, I would get H plus and Cl minus. So because this is producing, I don't know why they're ringing the bells. We're not on like, that's like the Thursday schedule. I wonder if they just didn't reset them from Thursday.
Because they didn't ring it.
Yeah. So the acid would be producing the hydrogen. Together, our Arrhenius bases, they do an acid plus a base, and you need to write this down, will produce salt plus water, H2O. Okay, so that's what they'll ultimately produce when they react together. And when we get to neutralization reactions, we'll talk further about salt, because they're not just talking about the kind of salt you put on your french fries. It's a whole class of compounds that are produced from acids and bases. But for now, that's the basic definition, that they're an acid plus a base is yielding a salt plus water. Okay? That brings us to the Bronsted-Lowry definition. Excuse me. Which is the most used definition. It's the one we're going to use the most as well. Okay? And its definition is slightly different, and it allows more things to be classified as an acid or a base. So the Bronsted-Lowry acid produces a proton, which is going to be an H plus, okay, but it produces a proton. Or it might produce that, remember that H3O plus, the hydronium. We use those interchangeably, okay, we use those interchangeably. So the Bronsted-Lowry base accepts the proton. So a while ago for the Arrhenius, we said that to be a base it had to be able to produce a hydroxide. This definition is saying as long as it can accept that hydrogen from the acid, it's considered to be a base. Okay? And then within this definition, we have something called a conjugate acid base. Okay? And it is a pair of compounds. They're going to differ by the presence of one hydrogen unit. Okay? So basically, I'll show you this in a second. It's going to be what's left, like after an acid donates a proton, its conjugate base is what's left after that happens. Okay? And so let's look at some further examples for that, because that's what your homework is going to be over today, is identifying. Okay? So the conjugate base, okay, come on, having some problems with connection here. The conjugate base of an acid is the remainder after the acid gave away its proton. Okay, so in this case, the HNO3 is the acid, it gives away its proton, and the NO3 minus, what's left, is the conjugate base. Okay, it will always be an acid and a conjugate base, or a base and a conjugate acid. Okay, and it's always going to be on opposite sides of the arrow. Okay, the conjugate acid can't write today. Can y'all tell that says acid? Sorry. I'm going to fix that. Is what's left over after the base accepts the proton. Okay? And so in this case, NH3 is a weak base. It can accept a hydrogen and become an NH4. So they go together. They're connected, opposite sides of the arrow. Now, I'm just showing you simply. When we're doing this, they're going to be in equations, because if we have an acid-base reaction, we have to have both the acid and the base. Okay? So let's do a couple of examples. Okay? So in this first one, we got HF plus water. And so what happens is the HF obviously is the acid, because normally we can recognize acids by what? Start with a what? Hydrogen. Okay? Normally, unless it's water. Water is different, which we'll talk about in a second. So what's left after the acid gives away its hydrogen is that F minus. Okay? So that would be its conjugate base. Okay? The water in this case went from H2O to H3O plus. So it accepted a hydrogen, so that makes it a base. So what's left after that is the H3O plus. So that would be its conjugate acid. So the first side of the equation is where you're going to call them acid and bases. The second side is where you're going to call it conjugate acids or conjugate bases. And you can abbreviate that with Ca and Cb. Okay? What you have to remember when you're doing this is you are adding or taking away a hydrogen. What is the charge of a hydrogen ion? +1. Okay? So that's why my HF went from being neutral to -1. Because what is 0 minus 1? -1. Okay? The water added a hydrogen, so it went from a 0 charge to a +1 charge. So when you're adding and taking away these hydrogens, you have to remember to also add and take away their charges. Okay? So let's look at HCl. HCl is going to be the acid. So which one is going to be its conjugate base? The Cl minus. So if it helps you to draw the lines, go ahead. You do not have to. I just like to show you how they're connected when we're doing that. And so in this case, the water accepted, so it's the base. And so what's left after that is this, so it's conjugate acid. Okay? For H2SO4, that's going to be the acid. And what's the name of that acid? Sulfuric acid, good job. And so what's left after it is the HSO4. So that would be its conjugate base. Okay? Notice that I left it as HSO4 and I put a -1 charge on that because it was neutral. I took away a hydrogen, so now it has a -1 charge. Okay? And then water, of course, is again going from H3O+. So this is going to be the base. And that's going to be the conjugate acid. Now the next one's a little trickier. Okay? The NH3 is going from NH3 to NH4+. So what did it do? Did it accept or did it give away a proton?
It
went from, these go together. Right?
I don't know.
It accepted. So if it accepted it, that makes it the,
Conjugate something.
no, not conjugate. On this side, it's going to be an acid or base. What do the bases do? They accept hydrogens. So this is going to be the base. So this would be its conjugate acid. Because it's a base on one side, it's a conjugate acid on the other side. The water did what? Water went from H2O to OH minus. So what did it do? It gave it away. So that makes it the acid. So that makes the hydroxide be the conjugate base. Okay? If you have H3O plus on the product side, it will always be the conjugate acid. Okay? On the product side, if you have OH minus hydroxide, it will always be a conjugate base when you're doing those. So if you see those, you can kind of take that to the bank, so to speak. Okay? What did you notice about water?
It's always.
It could be an acid or a base. Yeah. Here, right here and here, it was bases, but